assumption what was made by Wilkes is that no conditional output should be there. Why? Because say if the conditional outputs are there, so we need to have a output bit to decide whether it should be coming conditionally or unconditionally. So few of the outputs can be conditional and unconditional in the ASM. So unconditional is that in the stable state you are getting this as unconditioned, but conditional if you have, what is the extra burden to the network is that, or the circuit is that, there should be a decision making statement uh, where the command output bit should be specifying whether the true address or false address depends on the condition or not. That means it is it requires two instructions per the output. For single output, it needs two instructions, and it becomes a burden to the hardware. So that's why one aspect of Wilkes is that remove any conditional outputs, change them into a stable state so that you can make it as a perfect true address and false address. Between two state transition, you will be putting that micro instruction. So the whole of the instruction should be accommodated within that micro instruction. That is the concept of Wilkes. So still, if a betterment or a refining is to be done, maybe something like we can cut down this format into such a way that only one address will be there. Instead of true address and false address, only one address will be there, which is jump address. This is the refining.
Excuse me, ma'am.
Yeah.
Recording. It's meeting is not recording, ma'am.
Yeah. Oh, okay. Earlier format was that we used to get something like the index having the true address, false address, and your command outputs. Okay. So this was the format. So here what is the refinement we want to give is that instead of having two addresses, why not we put this into a single address, that is jump address. That means we need to define here when a state or when a transition should go to a jump address. If not jump address, what is the state it has to go? Is we define in such a way that the variable state variables what we are putting in for this refining or defining your states, it is given in such a way that something like this, say, sorry, test variable, if you take true address and false address, this is going to two states, say, because we don't have the conditional outputs. We are having only two elements, something like the stable state and the test variable. Okay, the conditional outputs as we used to represent in the earlier ASMs, what we seen in the this micro instruction format, or what you say a micro programming controller format. So at the most what you will be having is, if there is any test variable, that will be there, or if there is no test variable, directly say something like this, a simple example I'm taking, say state 0, state 1 and state 2 I'm taking. In this format, if you take uh, like in state is not, when x is true, that means x is the qualifier you are choosing based on your index value. The true address will be S1 and the false address will be S2. Okay, something like we were giving these values. randomly we were giving. Okay, any value you can give to your ABs, something like 0, 0, 0, 1, 1, 0 you can give, or you can give this as 1, 0, 0, 1 or 1, 1. Some value we were giving without any what you say conditions or any sort of restriction. But here, if we try to put this or refine this ASM, which will not have this true address and false address, rather we go for a jump address. Jump address in the sense, we try to take what is called as a qualifier bit in such a way that if the value of that qualifier bit, the value of the qualifier bit is equal, then the next address will be jump address. Else it will be the sequential address. What is the difference between jump address and sequential address is that sequential address is 0 will go to 1. That means something like 0, 0, 0, 1. 0, 1 sequential means 1, 0. 1, 0 sequential means 1, 1. If 2 state you are taking. 3 state if you take. 0, 0, 0 goes to 0, 0, 1. That means sequentially. That means in the order of 0, 1, 2, 3, 4 and so on it will be going. But jump address can be anything. You can say if a condition is satisfied, maybe take this 0 to 2 or 0 to 3 or 4. Any value it can jump to. This is called as jump address. That means defined by the design. Sequential means automatically 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5 in this sequence order. Okay, got this? Now, how to fix or how to fix these values of the state variables is now we have some condition. Something like if the qualifier value, that means based on say x of n is the qualifier, n is the index, which qualifier you are choosing, that value is equal to one reference bit we try to take. Reference bit we try to take. If that is equal to that reference bit, then the address will be jump address. Okay? Else it will be sequential address. This is the format of refining the microcode here. Okay? That means that we need to have this portion. What is your command outputs portion is invariant. This won't be changing. Only this portion we need to change now. From this format, we try to change this into a reference bit we are saying. A reference can be 0 or 1. Okay, reference can be 0 bit or 1 bit. Or else this is true false bit we say. 1 is true, 0 is false. So true false bit will be taken as the reference bit. So we define that true false bit, which happens to be the reference bit, and based on the value of the true false bit, if this is equal to the selected qualifier value, because once you select, say you are selecting something like the test variable, this one, x or y or z, based on n is equal to 0, 1, 2 and so on. Okay, and now the existing value, if x is say 0, I'm selecting n is 0, x value is 0 existing there. If my true false bit is also 0, what is the meaning of that is my x of 0 and the true false bit are equal. Okay, say another example, say I choose x and x of 0 is x, x of 1 is y, x of 2 is z. This is the way we are indicating the indices. Now see here, if n is 0 and the chosen x is 1, okay, then true false bit is also 1, then we say that x of 0 and the true false bit are equal. That means here x of 0 is 0 and true false bit is taken 0. Both are equal, then it is a jump address. Okay, or else it will be sequential address. So in that way, if I take 0, if I give here, say here, if I take 0, here there is no restriction saying that the first state should be given a value of 0. It depends on what is the type of ASM we are having and how many test variables you have and how many branches you have to divide. Based on that, you can start with any value, but see that wherever there is a test variable branching, there will be one sequential address and one jump address. Wherever there is test variable, one branching will be sequential, one will be what you say, jump address. Okay. Now say I take okay. Say if I take this as 0, what is the sequential address? 0 means it should go to 1. Na? 0 means it should go to 1. Say now I name this as 1, say. Obviously, the other branch will be jump address. It can be anything, either 2 or 3 or any number here. Okay. And in this condition, if you see, if I need to write the micro code, what should be my true false bit? See, x is 1. This is sequential if x is 1. Okay, 0 goes to 1 means this is sequential jump. Whereas 0 goes to any of the other value rather than 1 is a jump address. This is jump address path and this is sequential path. Okay. Now, when the jump address happens is when the qualifier value is equal. I'm taking x and with the true false bit, means that both are 0 0 or both are 1 1. X of n, true false bit is 0 or x of n is 1, true false bit is 1. Then the next address will be the jump address. Else it will be sequential address. So here this is our sequential path. This is our jump path, or what you say, jump address path. So x of the value of x is, because this is true means 1, this is false means 0. No? Your true false bit also will be 0. X is 0. Then this is jump address. Else it will be what you say, a sequential address. Okay. The other way also I can define. Say, if I take this as 2, I said you can take any other value. Okay, but see that it will be a branching of sequential and jump address. Okay, so 2 can be going to, say I name this as 3. Now this becomes my sequential jump address. This is sequential. If I take this 2, I take this 3, means that this path is sequential path. Now, this path should be jump address path. This will be jump address path. Means that I can divert these two, or I can name this as 0 or 1 or 4. Or, sorry, possible is 3 only, na? 0, 1, 2, 3. Now, what will be my, for this type of assigning, what is the value of x? X will be 1, na? This is jump address, na? this is jump address. True false bit should be 1. Then only this will be jump address. Else that happens to be the sequential 2 goes to 3. Okay. The other way also you can take. Say if I assign here 1, okay. If I assign here 1, I am showing all possibilities with a simple example. Say if this I take as 2, means that this is my sequential address path, and this becomes my jump address path. Means that, see here, 1 can go to 0 or 1, because 2 we have used here. Okay, so now x will be equal to, this is my jump address, this is my sequential address, this is sequential. So true false bit will be 0, x is 0, because this is the value. And until this is okay. If you have a qualifier, based on the qualifier value existing and the true false bit what is chosen, we are deciding whether it is a sequential jump or a jump address, or sequential address or jump address. Now, in this path, if you take, in this path, there is no test variable. This path doesn't have any test variable. Then how to take it? If any path is there where there is no test variable, we try to have one of the mux input, because earlier example or earlier micro instruction, this format we have implemented using 2 muxes. Now, in that, we, after choosing the qualifier, based on the qualifier x of n, we were having the values assigned and which decides what should be your value of the qualifier. Now, this we have seen. Here, what we do is, after choosing the qualifier, okay, we will be taking the qualifier values here. Now, what we do is, first value, we try to take it as, or what you say, first mux input, we try to take it as default true. True means 1. Why? Because, and let me complete this. Why? Because the other test variables will be taken through this now. Except the first one, the remaining inputs of the muxes will be given with one of the test variable. The reason here is, if there is no qualifier, or what you say, there is no test variable, which is now called as a qualifier for us, if that qualifier is absent, now how to take that, whether that true false bit is equal to or different from the qualifier? We don't have such arrangement. So what we do is, we try to take directly that true false bit to be equal to 1, make the true false bit to be equal to 1, and exclusively make n is 0. Now n is 1, n is 2, and n is 3, and so on will be given for x, y, z, and so on, whatever the qualifiers you have. N is 0 will be taken for a blank if that is used for no qualifier path. Okay, and this qualifier path, like here, we try to take it as a 1, make the true false bit equal to 1. Now what happens? For the qualifier n is 0, the value existing there will be true, means that 1. This defines that it is a jump address. It is a jump address. Okay, it is jump address now. Able to understand what I am telling now? how you are choosing the sequential address and the jump address? So people are there.
Can you once say again?
Ma'am, can you repeat again?
Which one? Repeat the process or repeat the question?
No, the process.
Okay, process I'll repeat, but at least one point is clear, stating that your jump path will be when the qualifier value and the true false bit value are equal.
Yes.
Okay. The other thing is when no qualifier is there, only the first bit of the mux will be taken as 1. The first
Yes.
input of the mux will be taken as 1, so that forcibly we are making the true false bit and the qualifier bit equal, so that it can be made as a jump address. It can be made as jump address.
Yes, ma'am.
Okay. So with these two basic understanding, we can now define one example. With one example, we can define all the statements, whatever we have given now. Okay. So let me have one ASM. Let me take. So altogether, how many states I'm taking? P, R, and S. This is X. This is X. This is Y. This is true. This is false. This is true. This is false. Yeah, done. Now, I'm taking, like we need only 2 variables to represent 4 states now. So what are the options available for us? Now see here. Here in this path of P to Q or S, P to Q or R, you have one in what you say qualifier X. And in the path of R to S, you have one more qualifier Y. And in the path of Q and P, or your S and your P, we don't need any qualifier. Okay. Or there is no qualifier. Rather, we can put that in that sense, saying that these paths should be jump address or sequential. Should they be jump address or sequential?
Which
No
one, ma'am?
qualifier.
So, jump address.
It should be jump address. Okay. So now let me have this different options we try now. Say if I take here this as 0, I'm starting with one way of assigning. Okay. Let us say I take this as the sequential line. Say this is sequential and this will be jump. Okay, jump. Okay, done. Next, one in the state of R, where it is like I'm taking the decimal representation of AB. Now, one should be going to a sequential This should be 2 because this is jump address. 1 going back to 1 is not sequential. 1 can go to 2 only. 0 can go to 1 only if it is sequential. So we are forced to have this as 2 if this is 1. We are forced to have this as 2 if this is 1. Okay, because this is our jump address, this is sequential one. Now this you can have 3 and 3 can go to any other state. That means 3 can go to either 0, 1, 2 and so on. And 2 is going, say it can go to 0, 1 and 3 because this is jump format. This is jump. This is sequential. Okay, so 2 can go to 0 because that is our jump address. Okay, the other way of assigning, let us take, say if you take this as 1, AB, I'm taking this as 1. Okay, say this, if I take, I'm taking one more path, another path I'm taking. If this I take as my sequential path, if you take this as sequential path, this will be the jump path. Okay, so if I take this as, sorry, 1 is going to, this is sequential, this can be anything, no? Say if I take this as 0, this 0 going back to 0 will be the jump address, this will be my sequential. Can I have that? No, no. Yes or no? Because 1 is used here, I cannot have 1 here. 1 is already used here, I cannot have 1 here. Right?
Yes, ma'am.
In that sense, I cannot take here 0. I can take this as 3. And this 3, can it be going to any other value which is in sequence? No. No, no. 3 can, like after 3, it can't be like more than 3, we don't have any available value. So this is not a valid assigning. That means you cannot take this state as 1. You cannot take this as 1. Maybe if you take also, let us try the other way. Say if this is 1. If you take this as the sequential address, this can be jump address. Okay, this can be jump address, and this value of 2 will be the jump address here, so this can be 3. Okay, 1, 2, 3. So now what is left over? 0 you can take here. So if you take this as 1, you cannot take Q as 2 and R as 3. So this is not valid. So some restrictions are coming over for assigning. Okay, let us attempt if we can take 2. If you take 2 here, okay, if you take 2 there, say I'll take this as 3, so that this is our sequential path. Can I have the other value happening here? This is jump path, okay. But 3 can never go, like both cannot be jump addresses. No, both cannot be jump. They should be sequential. So no, this should be sequential. So 3 I cannot take here. If I take green, I have say 2 if you are taking here. Take this as 3. This becomes your which path? 2 going to 3. This is sequential. this 2 can be going to 0 or 1. So if you take this as 0, you can have this 1. Okay, and this is okay. So what are the possible or valid assignings? What you have is this can be taken as 1 on condition that this q will be taken as 3. Okay. So these are all possible conditions I am showing. Okay, let me write a code for this is 1, 2, and 2. Okay. For at least for one assigning, let me write the microcode. Understood how we are forced to take these values now? Was it clear?
Yes, ma'am. There.
Now writing the microcode, how this will be done is, as I said, indexing n is 0 will be vacant, n is 1 will be taken as x, n is 2 will be taken as y, because 2 qualifiers we have. Okay. And how to implement this, I'll show you. This is index portion. This is your true false bit, refining the earlier microcode. This will be the jump address and your condition command outputs, whatever you have. Okay, listing this. Say what is the address you are in. You take first format. I will take this one. First 0, say. 0 means state P. State P, that is 0. What is the qualifier we need to select here is n is 1. This one is n. N is 1. And n is 1, see here, 0 and 3. This is your jump address path and this is your sequential path, 0. In green, whatever is written in green, this is the path for which I am writing now. So this true false bit, if I make it 1, then my jump address will be 3. And output 1 will be coming. Okay. Next. Q, state Q, not state Q, sorry. What is 1? 1 is R. R is 1 address. Now in this, again, we have a qualifier Y, which is equal to 2. So N is 2. N is 2. If you take the true false bit 0, jump address will be 1. Jump address will be 1 and the sequential address is 2. Okay, so we won't write the sequential address, we'll be writing only the jump address 0 0 1 0. That means out 3 will be coming out. Next, in this assigning 2 is S, S is 2. There is no qualifier here. No qualifier means n will be 0, where on that mux of 0, that will be made as 1. Okay, here n is 0 indicates that the value chosen here will be 1. I need to make this true false bit also equal to 1 so that I can define the jump address as 0 here. I can define the jump address because there is no qualifier. Must and should, that will be a jump address. Okay, now here what will be the output you will be getting is, and what is 3? Q is 3. Do we have any qualifier here? No. So your index chosen is 0, where true false bit is 1. true false bit is 1. That makes your jump address to be 0. And what is the output you will be getting is 2. Hope this is making some sense to you now. This is the microcode having a single qualifier, single address microcode. This is the single qualifier, single address microcode. Earlier with the true false bit, you have true address and false address. That is single qualifier per instruction. Here single qualifier, single address. There you had 2 addresses. Understood? Maybe if we write for the other assigning, say I write for this, let us have for this one. 2. For this, if you write the microcode, now 0 is Q. 0 is Q address here. There is no qualifier. So 0, true false bit is 1. Your jump address is 1. Jump address is 1 and out 2 is happening. And if you, this is another table I'm taking. Okay? And where is 1? 1, you have P. P is 1 here. Your index chosen to be 1. Okay? And your true false bit should be 0 or 1. 1. Jump address is 0 because this is the one. This is the path. Jump address is 0. There are out 1, 0, 0. 2. R is 2. Qualifier is 2 because Y is to be chosen. And your true false bit is 0. And your jump address is 2. Means that the sequential address is 3 here. And out 3 is generated. Now S is 3. No qualifier, N is 0. True false bit is 1. And what is the jump address? 1. And out 4 is generated. Is this clear? Is it making some sense now?
Yes, ma'am.
How we are taking the, like here we have some restriction, and that restriction is based on defining the path of the jump address and the qualifier, like true false bit. Path of the jump address and true false bit value. Any doubts you have? It's not that only we need to start with 0. That is one point you have to digest now. It's not that we need to start with 0. You can start with any value of your AB, but see that wherever the qualifier is there, you have 2 paths defined. One is jump address, one is sequential. Where there is no qualifier, we define that to be jump address. So there is no restriction. When there is no qualifier, blindly we can write anything. It can be a sequenced value or a jumped value, but we try to define the jump as jump address. We try to define it as jump address alone when there is no qualifier. So now here implementing this single qualifier, single microcode thing, it is earlier we have taken 2 muxes to define the choice of the qualifier and the qualifier value. But here in place of the 2 muxes, only 1 mux implementation to take. This implementation will be done using 1 mux and 1 counter Okay, in such a way that this counter will be either like whenever it is a sequential jump, or sorry, sequential jump means confusion, sequential address, it should be a counter plus 1. Whenever it is a jump address, it is to the counter given as the load address. Address will be loaded if it is a jump address. If it is a sequential addressing, it will be increment of the counter. So the counter will be used to implement such type of transition of the increment or loading of the address. And mux will be used for finding out the qualifier value. And your ROM will be giving the value of the true false bit value. Okay, so any programmable ROM can be taken, okay, which gives you the value of the index, the true false bit, and the jump address bit, and the command outputs. Okay, so maybe that 4 command outputs I'm taking here. Next, this qualifier based on the value of n. Here what we said is 0, 1, 2 and so on. The first one will be taken as one, that is true. The others will be fed by the other qualifiers, test variables in your design, x, y, z, so on. Okay. Now this gives you the value of x of n based on the value of qualifier and the value that is existing by the chosen qualifier. And this value has to be taken to an equivalence gate. What is this gate? XAND equivalence operator, which tries to take XAN of true false bit. This is going to give you a jump address. So this will be your jump address. And this jump address element should be taken to a counter. Now the counter, what you are using, will be having a load input. LD means load input. Okay. And complementing the count. When it is true, this is complement, like it will be given complement saying that you take the load address, complement, like you stop that incrementing the count. Okay. Or else if this is false, this will be true. These two are mutually what you say complements. When loading is done with the jump address, this will be stopped. When it is not loaded, it will be in sequential increment. Okay. So a counter tries to take these iterations, and whenever a load instruction is given, what is the address to which it should be jumped will be given by the, you say, the ROM what you are using. So what is the size of that jump address? That much size it will be, or that many D flip-flops or T flip-flops you can use here. And this is your Q, the counter output, the size. That means how many you are using, what is the size of the counter depends on what is the size of what you say, the address lines. How many bits of address lines you are taking. That will be fed to your ROM. Normally 74LS163 is the counter, I think I said earlier also. So this is the micro instruction control using counter based, the implementation using counter based. Hope you understood thoroughly regarding the microprogramming and writing the instructions. Yes.
Ma'am, can you say repeat about the counter again? How is the counter size determined?
Yeah, this counter size, like this is jump address will not be 1 bit, no? It will be of a set of bits, like based on what is the size of the address location or something like that, no? Based on how many bits you have, the address bits, that means that will be the size of the counter. Say 3-bit address, you are having 3-bit count. That means here the setup will be having, though we are showing only one, it will be, say, I'm taking this as say D of R. R is the count here. What is the count? This is total address. How many address bits are there? That many D flip flops we try to D, not D, T element counter. No, this is counter. Okay. That means we need to take the counter size 3-bit counter, 5-bit counter, or 10-bit counter. That counter size depends on the jump address bits, or what you say, address bits rather. Now, this address bits will be loaded onto each bit, will be loaded onto each register. Each bit will be loaded onto each register. Okay, so this is equivalent. This is not jump address that is provided. This is the condition that will be issued to the counter whether to load the jump address as described or as given by the memory location or increment the count. If this condition is, someone was talking, I couldn't hear. If this condition is true, that will be load. It will stop the increment. If this condition is false, that will be increment the count. That means sequential address, and the loading will be stopped. Say this is sequential address and this is your jump address. We need to provide both, no? Is this fine?
Yes, ma'am. For address, are we taking decimal values? Because we use 0, 1, 2, 3.
No,
Are we taking?
that ultimately will be in terms of the bit values only, no?
Okay.
AB means bit value. Bit value.
Okay.
Binary format. That's why the counter is taken. Counter will be in binary format, you know, for you. Will this be in binary format, counter? So we are just for understanding, we have taken the decimal representation, but ultimately when you implement, that will be in binary format. The counter will be in binary operation. No? When you take the outputs of all the binary outputs, it will be reflecting like this. You increment means you will be getting like this. No? So this will be binary format. So the size of this depends upon what is the address bits or how many number of address bits you have. Okay. Now, enhancing this control unit, something like a sophisticated microprogram sequencer is available for enhancing this element of the implementation of the micro code. Okay, so a sequencer available is 2910 sequencer, microprogram sequencer. Okay, that will be taking the selected inputs of the qualifiers and all, it will be issuing, it takes the input and it issues the next instruction address. Okay, means that like something you can visualize this setup as you have set of registers, okay, set of registers which stores the what you say, all the possible locations or all possible micro instructions. Because why I'm saying location is that every microcode or every element of the transition should be incorporated in the micro instruction itself. So all those will be residing in the registers, what we call them as pipeline registers. Okay. And and you have another set of registers, what we call them as writable control stroke. Writable control stroke, which stores the instruction address, next instruction address, and that will be sequentially be provided to the sequencer. These instructions will be given to the sequencer, and along with the architecture, whatever is used for implementing the whole setup, the sequencer and architecture will be like this will be issuing what is the value of n, okay, and that selected input of what you say x of n will be given by the architecture, and your set of pipeline registers will be issuing the value of the selected qualifier, okay, and based on this go to the setup of what we say the sequencer and the pipeline register. Okay, how this will be done is, if this is your setup of the architecture, okay, that architecture have this mux which takes or which provides the test inputs information based on the index value. Okay, and this gives you what is x of n. This will be going to the sequencer, 2910 sequencer. I'll show what is that internal to that. Okay, this sequencer will be giving an instruction or what you say next instruction address or next address instruction. You can take that way also. And this address will be taken to the writable control stroke. Okay, this is your address that will be taken, and these outputs will be fed to the pipeline registers. How many, whatever, or how many bits of address you have, that many outputs, and this is pipeline register. How many number of registers will be taken is equal to the number of bits in your address. That many D flip-flops will be taken, set of D flip-flops, which divides that portion into 3, as we said here. A portion of instruction that should be going to the sequencer, this is sequencer, and a portion where this is your test index, this is your test index. And this is to architecture, as we said, and this is also to architecture, where these are command outputs. Okay, this command outputs and the index will be given by the pipeline register. Okay, now how is this operating is that this microprogram sequencer, this portion, this microprogram sequencer, it have a point called as a stack pointer. What is this stack? What is the meaning of stack? Story? Is this story? Stack means stack pointer or stack set of registers only, na? Stack pointer indicates like first in, first out, or last in, first out, or first in, last out. You must have read this in your microprocessors or registry setups. Did you? Stacking means stacking means it is storing the say some program is running, main program is running. In between you bypass and you go to a sub program. Say once you go to a sub program in your main program, when you go to a sub program, when you are iterating, after completing the sub program, again it should go back to the point in the main program where it has stopped, where it got interrupted. Any intermediate interruptions happening should be going back to the interrupted point after completing that sub program or subroutine iterations. That means there should be one provision for you to store or to memorize what was the breaking point at which the main program was interrupted, and you have to give the address of that point. Okay, so that your program will come back to that interrupted point once it completes this subprogram. So that will be provided by the stack pointer. Your stack pointer gives you the information regarding all the addresses there. So this have 5-word pointer or 5-word stack, and whenever a main program is happening, it should be taking step-to-step iteration. That means an incrementer. A counter will be there in order to iterate the instruction one by one. So a microprogram counter will be there. All this I'm explaining that related to this 2910 sequencer. Okay, and this itself will be having some registers, set of registers to store the data that is provided by the pipeline registers here, this pipeline registers, or any subprogram routine interrupted addresses through the stack pointer. And these things should be performed, or iteration should be performed by using the program counter. Okay, so either you can have the transaction, or what you say transaction in the sense iteration happening from the data that is registered or stored in the registers from the pipeline, or the data that is stored in the stack pointer when the interruption is happening. Okay, so there is a need of choosing whether through the registers or through the stack pointer your data has to be coming in. Okay, so what is the provider, or what is the element which provides this information is your program counter. This program counter will be giving the information of the interrupted addresses and returning addresses. Okay, and this registry will be getting the data from the pipeline register. This one will be giving the pipeline through the pipeline registers, this data will become. So to have the choice or to choose one of the data provider, this what you say, the microprogram counter or microprogram sequencer will be having a multiplexer, to choose which one to be taken for accessing or iteration. So if say this is d of k size, I'm saying it is not 1 bit. So d of k is indicating that more than 1 bits. So this d of k is say your address. This can be one of the input. Parallelly, you can store that in this registers, what I said. Okay. And through that also, that means some return address sort of thing, if you need to have, you can access like direct or through registers. And this say stack pointer setup, if you have, through that the interrupted calls or interrupted addresses can be taken. So this is word 5-word thing that will be available on your microprogram sequencer. So the microprogram counter will be giving the address that will be stacked for the future iterations in place of any interruption happening. If not, it is a direct address. Okay, so this output will be of the same size as the size what you are taking here, and that will be yeah, hello. Ah. Yeah, just give me 1 minute, I'll come back. Just 2 minutes, I'll complete. Okay. So this output, this is the output. What will be the input for the counter? Then there should be a self-explanatory sort of thing. Like you have 4 sources of the instruction that can be taken by the sequencer. Okay. And here, you have a pass or fail of instruction that will happen. What is pass or fail is whenever a code is iterated, okay, or a request is sent, if the code is not available, then it will be a fail, or else it will be pass for iteration. So in this microprogram sequencer, what are the elements that will be available is this setup should be an instruction evaluation pass or instruction evaluation fail. That will be given by this. This is your output. Ultimately, this is your output, and this will be having these 4 setups, or what you say, 4 sources of instruction that is happening. And say something like, if I need to put this into a block format, what are the things available? So this is D of K, the direct input. This is your direct input from your pipeline register element. And based on the clock, it will be operating along with the pipeline thing. Okay. And you have the iterations selection, or what you say, selecting which one to be taken as the next address. That will be given by an instruction of I. 4-bit instruction will be given. Okay. And here you have an enabling signal, what is called as condition code enable. Condition code enable. I'll tell you what is this. This element of input along with what you say, the condition code will be making the iteration to pass or fail. Condition code. CC means condition code enable. Okay. Maybe this is one extra element. A carry in is there. For some other applications this will be there. This is for total 2910 I'm giving. And what are the outputs we have is indication of stack full and this Y output. These are the 2 outputs you have. Okay. Parallelly, many other outputs are available. Bidirectional iterations are available. Something like vector enable is there. Pipeline enable is there. And map enable. Map enable, all these instructions are extra, which we don't need for our microcode and all. Only what we are interested is about the clock, which is along with your pipeline registry setup only, it will be used. The same clock will be used here. And this condition code and the condition code enable will be making the instruction performance, or what you say, the operation of instruction to be pass or fail. Something like I said, when the condition code is taken and condition code enable is taken, when the enable signal is true and the code is not available, meaning is that when the condition code is enabled and the condition code is false, then it will be an operation of failure. Else it will be pass. That means when it is not enabling and condition code is not there, it is pass. When condition code is enabled and condition code is available, this will be pass. Okay, when condition code is not enabled and the condition code is available, then also it will be pass. Okay, only one condition where the iteration will be fail is that when the enable signal is true and the condition code is not ready in this, any one of the source is not ready for the instruction, then it will be fail. Okay, this sequencer will be used for issuing the next address. This is why. This Y can be chosen from any one of the source model. That's what we are saying. Okay. So this is about your microprogramming and microprogram sequencer concept. So altogether in this microprogramming, we have taken the single qualifier, single state instruction, where earlier it was multiple qualifier representations. Okay, we refined that into single qualifier per state instruction. Then later we refined it into a single qualifier, single address micro instruction. Implementation of that is using a what you say, a coincidence logic along with a counter. That will be taken, or what you say, that control unit is used or is using this microprogram sequencer. Okay, so until this will be your bit portion. Until this will be your mid portion. Okay, any doubts you have, you can get them clarified. If no doubts, we'll close the session. Yeah. Dheeraj, Sai, Varun, both of you are there? Dheeraj and Sai.
Yes, ma'am.
Yeah. Evening, see, I'm cautioning you at the beginning itself, like DSD1, if there is mass copying or copying of any sort, this time failures will be given as failures. I won't take any consideration. Okay?
Okay,
No
ma'am.
sort of mischief, no sort of copying should be done by any student, and you don't give any excuses. If I don't entertain any excuse in this time, it will be zero means zero. That's all. You don't argue. Anyone should not argue. No one should send me any mails, or no one should send me any messages. Okay, because whole of the class is there. Through CRs, I am conveying this to whole of the class now. Okay, and through LMS only answers will be considered. Through LMS only answers will be considered, and there won't be any remit or reminer sort of thing. You have to write the exam. That's all. Is this clear? So 5:30 to 6:10 will be the exam. 10 minutes is for grace time. Half an hour is exam. Okay, so 40 minutes will be for total duration of your exam. Okay.
Okay, ma'am.
Okay, 5:30 to 6:10. Okay.